This is ECE 471 in 19 summer, and as one of the supplemental materials for the course, I'm providing some videos for particularly the calculation examples given in the class. Hopefully this will become an alternative way for you to better master the knowledge, the calculation especially. So to topic 1, we have power calculation examples given in the lecture, and today we just repeat those examples given in the lecture already, and we're going to go through example 1 and 2. So example 1 is a very straightforward circuit. We are seeing one single phase voltage source feeding one load, and the voltage is given as a function of time t, and the load is in phasor. So find instantaneous, active, reactive, and apparent power for the load, as well as the power factor of the source. So a little bit tricky thing about this example is, and also the thing you need to learn is the conversion between the time function and the phasor. Okay, and the general workflow is actually you have to convert all of the given parameters into phasors, and then conduct whatever circuit analysis and calculations in terms of phasors. And here we might apply all of the principles we learned from circuit class, like Ohm's law, voltage or current dividers, and KVL or KCL, and then from there we can find whatever voltage or current we need for calculating the power. And then from the power, we need to be very clear. The power calculation formula is apparent power S in phasor is equals to the voltage in RMS value phasor times the current in RMS value conjugate. And of course, because the voltage and current are both in phasors, the resulted S apparent power is also a phasor, and then we can convert this phasor to the equivalent complex number, which going to tell you the active and the reactive power as real part and imaginary part respectively. Okay, this is the general workflow we want to follow, and this power calculation is generally conducted by your calculator. Okay, we don't have to use hand calculation. So in terms of the calculator using, you obviously need to know how to input the phasor values, how to input complex numbers, how to conduct the operations among them, and how to convert the phasor to complex number, and the other way around. Okay, so to this particular problem, there might be more than one way to solve it, but I just directly go to the current by following the Ohm's law, obviously. So the voltage divided by the impedance, and the voltage here, as we already said, need to be converted to a phasor from the given time function. So we are using 100, the magnitude, or say the peak value, with phase angle of 0, divided by the given impedance in the denominator, and end up with a current with magnitude of 80, phase angle of -60 degree. So with the phasor current, we can go ahead to calculate apparent power, which is equals to the voltage phasor RMS times current phasor RMS conjugate. And as we already said, we need to use the RMS value. That's exactly why we have this 2 square root 2 here now, because both 100 and 80 are the peak values, so we need RMS value, so we divide by square root 2 for both voltage and current. And due to the conjugate here, the -60 degree becomes positive. So by this operation, we end up with the apparent power, and from which we can easily tell actually the active and the reactive power as the real part and the imaginary part. Here, of course, you want to be very careful about the unit. Okay, the unit. The unit for apparent power is VA. The unit for the active power is watt, and unit for reactive power is VAR. Okay, and also you can tell the workflow is actually we are looking for the apparent power directly, from which we can easily tell the active and the reactive power. Okay, rather than the other way around. Okay, so go to the apparent power directly. The last power we need to find is the instantaneous power, which is equal to the product between the voltage time function and current time function. So the voltage time function is already given here. So what we need to do is just to convert the current phasor here to a time function down here, which is end up with 80 as magnitude, or say the peak value, and times cosine omega t minus 60 degree as the phase angle, times the voltage time function, end up with the real-time instantaneous power, which is a function of time t as well. Okay, these are the power. At last, the power factor of the source. Actually, there are at least two ways to find out the power factor. One way is based on the phase angle, another is based on the apparent power we just obtained. So first of all, let's try the phase angle. So based on the voltage and the current phase angles, we can find so-called impedance angle equal to the difference between two. So cosine of this impedance angle equals to the power factor. Here, be careful, the impedance angle is equals to the voltage phase angle 0 degree minus the phase angle of the current, which is negative 60 degree. So end up with a 0.5. However, never forget to provide information about lagging or leading, which could be told by the sign of the impedance angle. If it is greater than 0, it is lagging, otherwise it is leading. The second way to find the power factor is based on the power, apparent power. 2 plus 2 square root of 3j kilo VA, and from which we can easily apply a division between the active power and magnitude of apparent power. Be careful here, is magnitude, which is equals to square root of real part square plus imaginary part square. Okay, so we are ending up with same value, 0.5, and here the lagging or leading information could be told by the sign of reactive power. If it is greater than 0, it is lagging, otherwise it is leading. Okay, this is the example 1. And now we are following basically the same idea and workflow to solve the example 2, in where the voltage source is given in RMS value, very nice, and also phasor, feeding 3 parallel loads Z1 through Z3. Okay, the questions are basically saying find 4 different powers and the power factor. Again, there's more than one way to solve this, and I'm using directly the current. So I'm looking for the current for each one of the load. So to Z1, I have voltage cross it divided by impedance of it equals to 20 with angle of 0 degree ampere. This is the current through Z1. Similarly, I got I2 and I3 for Z2 and Z3 respectively. Again, same voltage in numerator. and different impedance in the denominator. So I got 3 currents, based on which I can go ahead to find apparent power. As we said, always directly go to the apparent power. So S1 equals to V times I1 conjugate. So we need RMS value in this formula, and the given 1200 as well as the resulted current are both in RMS value. Very nice. So we got apparent power. And similarly, S2 and S3 in same pattern. V times I2 conjugate, V times I3 conjugate, respectively. We got different apparent power. So again, we can easily tell the active power and the reactive power based on the apparent power. So to the instantaneous power, we need to do a little work. So the given voltage is in phasor, so we need to convert it back to time function, which is equals to 1200 square root of 2 times cosine omega t. We know the angle, phase angle is 0, and we know the magnitude is 1200 RMS. That's exactly why we need to times square root of 2 to make it become magnitude, or say the peak value. And the current time function is from here, from the current phasor, 20 with 0 degree angle, and then you convert it to 20 times square root of 2 cosine omega t. Okay, so keep cosine or sine same as the voltage. Okay, keep them consistent. And also we know the current frequency is same as voltage frequency, so they are having exactly same omega here. Following the same procedure, deal with P2 of t and P3 of t. Okay. So these are the instantaneous power. At last, the power factor. I'm just use the total apparent power to deal with the power factor, looking for the power factor of the source. So we are looking for the source power, which is equal to the summation of 3 load powers, obviously. So which end up with 96 plus J 72 kilo VA, from which we can calculate the power factor. Again, active power, real part, divided by square root of 2 of real part square plus imaginary part square. Be careful here, we are not including the J here, okay? Otherwise, you're going to have a negative sign in front of it. So ending up with 80% power factor. No, and lagging can be told by the positive sign of the reactive power here. This is the positive reactive power, so it's lagging. Okay, that's all for this single phase power calculation examples for topic 1. Thank you.